Arcs and chords. Theorem 9-2. In the same circle or in congruent circles, equal arcs have equal chords, and equal chords have equal arcs. Since chord CD is equal to chord AB, since chord CD is equal to chord AB, they're both 4, then the arc of chord CD, which would be arc CD, would be equal to the arc of chord AB. The arc of chord CD, arc CD, is equal to the arc of chord AB, arc AB. Now that means two things to us. It means that their arc measures are the same. It also means that the lengths of the arcs are the same. Okay? So in the same circle or in congruent circles, equal arcs have equal chords, and equal chords have equal arcs. Theorem 9-3. If a radius or diameter is perpendicular to a chord, then it bisects the chord and the arc of the chord. Now, we're going to start with the chord here, chord EM. If a radius or diameter, so we got to go through the center, is perpendicular, that means it hits at 90. If a diameter or a radius is perpendicular to a chord, then it bisects the chord and the arc of the chord. Well, how do we know that? Well, we know that because of the isosceles triangle theorem. HE and HM are radii of the circle, therefore they're equal, therefore this is an isosceles triangle. We have the perpendicular, the 90 degrees. That's 2 out of the 4 things that we need for an isosceles triangle. So that proves to us it's isosceles and that the green thing is the bisector of the vertex angle, the bisector of the vertex angle. The isosceles triangle theorem says that the bisector, I'm going to draw this bigger. That wasn't good. Let me start again. The bisector, I missed again, one more try, bear with me. The isosceles triangle theorem says that the bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint. Now, what we see marked in the circle down there is the 90 in green and the fact that it's isosceles in red. We have 2 out of those 4 things, so we can automatically conclude that the other 2 are true. One of those conclusions is that the chord was bisected. This little piece equals this little piece. Now, these 2 angles, that's the vertex angle bisector, so those 2 angles are equal. If those 2 angles are equal, then this chord right here is equal to this chord right here. So not only did the chord get bisected, the arc of the chord got bisected. So if a diameter or radius is perpendicular to a chord, then it bisects the chord and the arc of the chord. If a radius or diameter is perpendicular to a chord, then it bisects the chord and the arc of the chord, and that is based on the isosceles triangle theorem. Okay? So since HM is perpendicular, we're right here. Since HG is perpendicular to EM, that means that EG is equal to GM, and arc EX is equal to arc MX if the radius is perpendicular to the chord, then it bisects the chord and the arc of the chord. Reason, EHM is an isosceles triangle because EH and HM are radii. Triangle EHM is a 30, 60, 90 triangle. How do we know that? We know that because of the relationship here between the short leg and long leg. The formulas for 30, 60, 90 triangles are the long leg equal short leg times the square root of 3. Since you see that relationship here, the short leg was 3 and the long leg is 3 square root 3. That looks like a 2, but it's a 3 square root 3. Then we can say that it's a 30, 60, 90 triangle. EH is going to be 6 because the hypotenuse is equal to the short leg times 2. Angle EHG is 60 degrees because it's the angle opposite the long leg. Arc EX is 60 degrees. If that angle is 60, then this arc is 60. Let me clean this up just a little bit. Maybe I should blow this up. Let's wide out that and go to the blown up version because I'm afraid it may be a little bit hard for you to see, and I've got a blown up version right there above it. So here's our blown up version. And we've got this arc sitting out here. And we're going to extend that radii. We had a relationship here that this was 3 and this was 3 square root 3. Long leg equals short leg times the square root of 3, so this must be a 30, 60, 90 triangle such that the short leg 3 is opposite to 30 and the long leg 3 square root 3 is opposite to 60. This angle 60 was the central angle, so it's equal to the measure of its intercepted arc. If that angle 60, then this angle 60 because that was the vertex angle bisector, so this arc is 60, so that whole big arc is 120. These are the things we're saying down here. So then arc EXM, and I got to go back and find my picture now. I guess that's the whole thing I forgot is 120 degrees, I'm assuming. Let me wiggle it so I can find it out. That's right. Arc EXM was 120 degrees. Okay. Any questions on that? If a diameter or radius is perpendicular to a chord, then it bisects the chord in the arc of the chord. Okay. Theorem 9.4. In the same circle or in congruent circles, chords equally distant from the center are equal chords, and equal chords are equally distant from the center. So in the same circle or in congruent circles, chords equally distant from the center are equal to one another, and chords that are equal to each other are equidistant from the center. Distant from the center. What's that talking about? Equidistant from the center. Well, that takes us back to the definition of the distance from a point to a line. The distance from a point to a line is not crooked. The distance from a point to a line is defined to be the length of the perpendicular segment drawn from the point to the line. So when we say equidistant from the center, we're saying that the lengths of the perpendicular segments drawn from the center to the chords are the same. Okay? All right. So the distance from chord AB to the center is the length of that perpendicular segment 3. The distance from chord HF to the center is the length of that perpendicular segment 3. Those are equally distant from the center, therefore they're equal chords. So EX, which is 3, is the distance from chord AB to the center point E. EY is the distance from chord HF to the center point E. Since EX equal EY, they're both 3. Since they're both equally distant from the center, in other words, then chord AB must be equal to chord HF. The length of chord AB is equal to the length of chord HF. Now, once we get those right angles, we got to think about right triangle geometry, isosceles triangle theorem, because of equal radii. But we get the right angle and we start thinking Pythagorean theorem, special right triangle rules, sine, cosine, tangent. Okay? So, let's backtrack a little. In the same circle or in congruent circles, equal arcs have equal chords and equal chords have equal arcs. If a radius or diameter is perpendicular to a chord, then it bisects the chord and the arc of the chord. In the same circle or in congruent circles, chords that are equally distant from the center are equal, and equal chords are equally distant from the center. Examples. Daily work 9-4. Not examples. Daily work 9-4. Now, let's just look at numbers. Let's just do number 3 through 7. We'll play with that one. Get some of this out of the way so we can just kind of focus on that. It's got some notices there, but we're just going to notice it on our own. Bear with me as I clean up. I want to be able to focus on just that one problem. Okay. What we have is we have a radius that is perpendicular to a chord. If a radius is perpendicular to a chord, then it bisects the chord and the arc of the chord, which means that that piece equals that piece, and this whole chord equals that whole chord. Okay? So, we want FG. Well, how are we going to get FG? Well, let's blow this thing up. This is 8. This is 4. We're looking for FG. We can call it X. We're looking for our missing side of a right triangle, so we can use the Pythagorean theorem. C squared equal A squared plus B squared. But even better than that, we should know the relationship because we see the 4 to 8. But let's act like we didn't see that yet. So we're going to say hypotenuse 8 squared equal one leg x squared plus the other leg 4 squared. And so we're going to square those and get 64 equal x squared plus 16. We're going to undo addition by subtraction. And so we're going to have x squared is equal to 48. We undo the square with the square root, and we get x equal, but 48 doesn't have a perfect square root. If we can think of it as the product of its largest perfect square factor and the one that would go with it, 16 times 3 is 48. The square root of 16 is 4. We would get 4 square roots of 3. 4 FG. Now, the chord got bisected, so that's half of chord EG. So the whole chord EG would be 8 square root 3. If that didn't work for you, then we would have to take that 48 and do the prime factorization. Rewrite it as the product of its primes. Circle sets of 2 for square root. Make a new radical. From each set, we bring a number out. What didn't get circled goes back in. We multiply the outsides, multiply the insides, and we get 4 square root 3. So there's the prime factorization method of getting that 4 square root 3. Angle DGF. Angle DGF. Well, how are we supposed to know that? Well, it turned out that this was 4 and 8 and 4 square root 3. You should be able to see the relationship if you divide by 4. Of 1 to 2 to the square root of 3, which is the numbers that we memorized for a 30, 60, 90 triangle. And so that should tell us that angle DGF is 30 degrees. Arc GH. If the angle here is 30 degrees, then the angle here is 60 degrees, and arc GH is equal to the angle at D, which is 60 degrees, because the central angle is equal to the measure of the intercepted arc. So if that was 60, then this is 60. That's half of a bisected arc EG, so arc EG is 120 degrees. And so we thought back to the Pythagorean theorem. We thought back to that relationship of 1 to 2 to the square root of 3. And we were able to say, well, that's 30 degrees and 60 degrees because it fit that relationship we memorized of 1 to 2 to the square root of 3. Well, you may say, well, that didn't hit me. So what am I supposed to do if it doesn't just hit me? Well, if it doesn't just hit you, you'll have to use a trigonometric ratio. Example. Let's go back to this picture. I'm going to clean it up just a little bit. What we were trying to do is find that angle of 30 degrees. And we knew the information that's up there by using the Pythagorean theorem. And we don't know that that angle's 30, and we're trying to figure that out. So we'd say, well, what is angle DGF? Well, we want a trigonometric ratio, so we'd write down angle DGF equal. That's the angle we're looking for. We take the sides that we have and see how they're related to the angle that we're using. The 8 is the hypotenuse. The 4 is a leg. It's the leg opposite. Leg opposite, hypotenuse is sine. So we could say sine angle DGF equal. And then we need a fraction. To get the fraction, we do what sine says. Sine says leg opposite 4 over hypotenuse 8. And so we have sine angle DGF equal 4 divided 8. 4/8 is a half, or 0.5. We want to get rid of the sine function. We get rid of that with its inverse function. So we use the inverse sine function, or sine -1. And so we're going to go to the graphing calculator and do inverse sine 0.5 close, and we get 30 degrees. Notice it's still on float force. It's going to throw those zeros there even when we really don't want them. And so inverse sine function cancels sine function, and we have angle DGF is equal to 30 degrees. So if you didn't see that 1 to 2 ratio between the short leg and hypotenuse and realize that it was a 30, 60, 90 triangle because of that, then you could set up a trigonometric ratio to find an angle measure and go from there. Any questions on that? Okay. So be looking for special right triangle relationships. Be looking for Pythagorean theorem as you solve the problems on that page. Okay. Let's look at the bottom. Let's just do 18 through 20. Arc ACD. You may say, well, how do I find arc ACD? That's a major arc because it's 3 letters. It's not from A to D the short way. It's going to be from A to D the long way. A circle's 360 degrees. The minor arc was 75. The minor arc in red. The major arc in blue is everything besides that. So it would be 295 degrees for a major arc ACD. That would be 285. I subtracted wrong. Sorry about that. Arc AB. This chord is equal to this chord is equal to this chord because they all had one mark. And equal circles are in the same circle. Equal arcs have equal chords. Therefore, arc AB is equal to arc BC is equal to arc DC. The sum of all three is 285. So to get the measure of each one, we would take that 285 divided by 3. 3 sevens are uh, 3 nines, excuse me, are 27. With 1 left over, bring down a 5. 3 goes into 15 5 times. You get 15 with 0 left over. And so we get 95 degrees for arc AB, arc BC, and arc DC. It wants arc ADC. ADC would be from A to D to C. If you add those up, you get 170 degrees, which means we should not have named it arc ADC because it didn't add up to more than 180, which means it's a minor arc, so we should have properly called it arc AC. Any questions there? Okay. And there's some more to play with. You just need to have to dig through some of these. The odd answers are in the back, so you're going to find some more solutions back there if you get stuck. Number 26 says, draw a circle with radius 12. Draw a chord 6 millimeters from the center parallel to the radius. How long is the chord? Let's think about that. Now, I want you to actually draw it accurately. I'm just going to show you kind of what you're going to have. You're going to have a circle with a radius of 12 millimeters. If the radius is 12 millimeters, then the diameter would be 24 millimeters. It says draw a chord that is 6 millimeters from the center parallel to the radius. How long is the chord? How long is the chord? You may say, well, how could you do that? Well, if this radius is 12, then we could draw a radius right here that was 12. And if I pull out that little triangle here, then this is 6, and this is 12. And so I could do the Pythagorean theorem, c squared equal a squared plus b squared. 12 squared equal a squared plus 6 squared. 144 equal a squared plus 36. Subtract 36. A squared is equal to 108. Undo the square with the square root. Break down the 108. Circle sets of 2 for square root. Make a new radical. From the set of 2's, you bring out a 2. From the set of 3's, you bring out a 3. That 3 on the end wasn't a part of that circle. My circle went wild. That 3 goes back in. And so we multiply and get 6 square root 3. So this is 6 square root 3. If a radius is perpendicular to a chord, then it bisects the chord in the arc of the chord. So that is 6 square roots of 3. So the length of the whole chord is 12 square roots of 3. Lots of stuff happening in there. Lots of stuff happening in there. Got to know the whole geometry book and be able to think through all the little pieces of everything we've ever learned. We got parallel lines going on there. We got if a transversal is perpendicular to one of 2 parallel lines, it must be perpendicular to the other. We have all of the radii in a circle are equal, so we're drawing radii all over the place. We've got if a uh, radius is perpendicular to a chord, it bisects the chord in the arc of the chord. Got some 30, 60, 90 triangle stuff going on if you think about that relationship. These are in the ratio of 1 to 2